Okay, today we are going to learn open circuit tests of the transformer. So first, the transformer can be tested in three ways. One is the open circuit test, short circuit test, and polarity test. So today we are going to learn about two tests, that is open circuit test and short circuit test. Okay. So why we have to conduct these tests? So by conducting these tests, we can model the equivalent circuit of the transformer in any way. That is, we can determine the parameters of the transformer by using these equivalent these tests. So by using this, we can analyze the transformer at any load. This is the main purpose of the conducting tests of the transformer. Okay. First one, consider open circuit test. Open circuit test. So in a transformer, we will normally use step up or step down transformer. Not we will use same number of turns on primary and secondary in the power distribution systems or power systems, because these one-to-one transformers will be used in the communication circuit to distinguish the source circuit and the load circuit, or to separate electrically, to isolate the electrically load and source circuit. So normally we will use step up or step down transformer. So open circuit test is conducted on the LV side, because so it is conducted on LV side. See here, whenever consider an example transformer 11 kV bar 400 volts transformer. So this is a transformer. We have to conduct the test, that is open circuit test. So if you connect the meters in the HV side, you have to open circuit the LV side. If you connect the meters at the LV side, then you have to open circuit the HV side. See here, what is the advantage? Means either side you can connect the meters and secondary side is open circuited. So in the same way, in both of the cases, you will get the same parameters of the transformer. But by connecting the meters at the low voltage side, we can use low rating meters of the transformer. Low rating meters means there is in this open circuit test we will use three types of meters, that is voltage meter, current meter, and power meter. Means voltmeter, ammeter, and wattmeter. These three meters are used here. So we will prefer these meters connected to LV side. So here we will use 400 volts voltmeter, and of course the current is somewhat high, because at the no load test only exciting current will be flowing. That's why we will use low rating ammeter and wattmeter also. So here we will use low power factor wattmeter, because at no load the exciting current here, see here, I0, IC, IM. This power factor is approximately equal to 90 degrees. Since if you neglect the resistance, or if you neglect the no load losses or RC, then exactly I0 is in phase with IM. So the power factor is about 0, nearly equal to 0. So that's why we will use low power factor meter here. Then the open circuit test gives the shunt branch parameters. So usually the circuit, equivalent circuit, previously we have discussed na? So that can be approximated, or approximate circuit we will use that. So primarily exact equivalent circuit is this one. See here, this is exact equivalent circuit. This is R1, X1, R2 dash, X2 dash, RC, XM. So if you move shunt branch parameter either side, at source side or at the load side, you can approximate this this equivalent circuit to somewhat legible way. So that is, if you shift this parameter to this source side, then you will get this equivalent circuit. So this, since this source side is voltage constant, you can neglect this branch, and here X is very greater than R, so you can simplify this circuit to simple unreactance circuit. So here is one doubt will arise, why we will shift this shunt branch parameter to source side, not on the load side. So you can shift the shunt branch parameters to load side, but see here, so by shifting the shunt branch parameter to the source side, this much amount of voltage drop is neglected. Means while you are calculating the voltage regulation, or somewhat in that cases, this much of drop we have neglected and simplified the circuit. Okay, if you shift this shunt branch parameter to the load side, this much of I naught into this total drop we have to consider. So this is a somewhat erroneous condition. So this is worst condition, and the voltage across the shunt branch parameter at the source side is constant, but the voltage across the shunt branch parameter at the load side is not constant. So we have to represent this in the load side. So this is not valid for this case, and this is not. So that's why we have to shift the shunt branch parameter to the source side. This is one case. Okay. Now, why we have to neglect these two parameters and we will get only shunt branch parameter in the open circuit test? So here in the open circuit test, the secondary is open circuited. This is equivalent circuit, approximate equivalent circuit we have got. This is it? So this current is I2 dash. This is ZE, equivalent impedance. Since secondary is open circuited, I2 dash is equal to 0. So we can neglect this entire branch and simply we will get one circuit, that is this shunt branch circuit. RC XM. So while measuring U at the low voltage side, we have connected the meters and we have applied rated voltage at the low voltage side, and we will record the meters reading, that is P0 voltmeter reading, I0 current meter reading, and P0 wattmeter reading. So by using these three parameters, we can conclude, we can get the values of RC and XM. How we can do this? So first one, we have the values of I0, V0, I0 and P0. So P0 is equal to I0 V0 cos phi naught, is it? So no load power factor. So we can get cos phi naught is equal to P0 divided by I0 into V0. is it? So we have got the cos phi naught. Now see this figure again, I naught, phi naught, IC, IM. See here, IC is equal to I naught into cos phi naught. Is it correct? IM is equal to I naught into sin phi naught. And see again this equivalent circuit. Remember this. This is voltage applied, RC, XM, I naught, IC, IM. Okay. So can I write RC is equal to V divided by AC? Is it? So current is flowing in RC is IC. So V is constant. So RC is equal to V by RC, IC. That is equal to V naught divided by, what is the value IC? I naught cos phi naught. We know the I naught, cos phi naught and V naught. So we will get the value of RC. Similarly, XM is equal to V naught divided by IM. That is equal to V naught divided by I naught sin phi naught. We got the values of RC and XM, shunt branch parameters. Okay. So from the no load test, we will get the shunt branch parameters. How we can get the series branch parameters? That is RE and XE, entirely ZE. So this can be solved by SC test. Okay. So SC test, short circuit test. In short circuit test, either one of the terminal is short circuited and the in other terminal we have to connect the meters. So which terminal is preferred to short circuit? So usually at low voltage side we will prefer short circuit. Short circuit means we have 11 kV bar 400 volts. Now we have in open circuit test, we have open circuited 11 kV side. So we have connected the meters at the 400 volt side. Now SC test is preferred at high voltage side, high voltage side, and the meters are connected at the HV side, and the low voltage side is short circuited. This is the case of short circuit test. So here the meters are connected at HV side and LV side is short circuited. Here the rated current at the short circuit terminal means, see here, this is a transformer. We have short circuited secondary. This is say 400 volts. This is primary. We have connected a meter, voltmeter and power meter also. So wattmeter. So here what is the rated current at the secondary? Say it is about 20 amps. Is it? So what is the rate? Say it's taken 20 amps. So we have to adjust the primary side until the 20 volts is obtained, 20 amps is obtained at the secondary side. So here we have taken a auto transformer. So adjustment. So you adjust the wiper and see the current at the secondary side. If the current at the secondary side is 20 amps, then take the meter reading of ammeter, voltmeter and the power meter, wattmeter. Okay, this is the procedure of conducting the AC test on the transformer. So here at the primary we have rated voltage of 11 kV, but we don't apply the 11 kV at the primary side because secondary side is short circuited. So if you apply 11 kV at the primary, this entire winding will be damaged. So this current is not 20 amps, not the rated current. It will be beyond the rated current. So that's why this winding will be damaged. So entirely the transformer will be get damaged. So that's the reason. So we'll apply normally 6 to 8% of the normal voltage. Okay. So this is all about the AC test. We will prefer this is it at HV side. The meters are connected at HV side. Why we will prefer the HV side, the meters? Because at the HV side the voltage is applied, that is low voltage, not at a rated voltage 11 kV volts, and the current is also minimum, because see at low voltage side high current will be obtained. So at the HV side low current will be obtained. So meter is somewhat high power factor meter will be used. This is the concept of SC test. How we will get the series branch parameters from the SC test? Here we apply the voltage VSC, ISC, will record the readings of the current, and PSC, power, short circuit power. Okay. Now can I write ZSC or Z equivalent? So this Z equivalent is obtained which side is meters are connected. So here HV side is meters are connected. So this is the equivalent impedance referred to HV side, that is equal to HV, write it here, VSC divided by ISC. Now the power PSC is equal to ISC square into RE. This is also, this equivalent resistance also at the HV side. So RE HV is equal to PSC divided by ISC square. This is all about RE. So now we can write XE HV is equal to root of ZSC, means ZHV, ZEHV square minus REHV square. So we have determined the parameters of series branch parameters. Now for determining the voltage regulation, we will need only this SC test, not open circuit test. So remember this, for voltage regulation we need only SC test. For determining the efficiency of the transformer, efficiency eta, we will need SC and open circuit test. Both tests are required. This is all about the testing of the transformer. Okay, we have two problems. See here, see the problems. First one is, this is all about circuits, open circuit and short circuit test problems. See, first one, here he has given R1, R2, X1, X2 and RI, RC and XM. These parameters he has given. First we have to find open circuit current, power factor when LV is excited at rated voltage. See, open circuit means we have taken only shunt branch parameters. So shunt branch parameters are, he has given Ri is equal to 10 kilo ohms, Xm is equal to 1.6 kilo ohms. So now I'll write I naught is equal to bar is equal to IC bar plus IM bar, that is equal to V divided by RC minus J V divided by Xm. Is it see? Understand this current. This means here J is Xm, J Xm will come, so multiply on both sides, J will get minus J. Okay. Now we know the V and RC, V and Xm. Open circuit test, we will get the rated voltage at the low voltage side. So what is the low voltage side? So he has given low voltage 240 volts. So 240 divided by 10 into 10 power of 3 minus J into 240 divided by Xm 1.6 into 10 power of 3. Okay, what is the value of current here? That you have got is 2.4 minus J into what is the value here? No, we have done mistake. We have done mistake here is, though open circuit test is conducted on the LV side, is it? Meters are connected at the LV side. So he has given Ri and Xm in the HV side. So we have to refer these values at the LV side. Is it? So we have to refer these values at the LV side. So what is the K value we have to find? So K is equal to 2400 divided by 240. Is it? That is equal to 10. So for LV side we have to divide, means we have to reduce the resistances or impedances. So that is R2, R1 dash is equal to 10 into 10 power of 3 divided by 100, is it? So that is equal to 100 ohms will come, and Xm is equal to 1.6 into 10 power of 3 divided by 100. So that is equal to 16 ohms will come. So here we will get 100 ohms, here also 16 ohms. So 2.4 minus J into 15 amps. So if you write this in polar form, you will get 15.191 at an angle of minus 80.91 degrees. So what is power factor? Cos phi is equal to cos of 80.91. What is power factor here? 0.1579. This is power factor, and this is the problem of A, first section. See the second section. B. He has asked to find, now see once again I will read this. The voltage at which the HV side should be excited to conduct a short circuit test LV side with full load current flowing. What is the input power and its power factor? So here the second section is about short circuit test. So we have to find VSC. So he has given rated current means ISC. So we know the ZSC. Yes, we know ZSC. He has given R1, R2. So then we will find ZSC. First find the rated current. Okay, so rated current is equal to 150 into 10 power of 3 divided by 240, that is equal to 625 amps at LV side. Is it? So then find this or refer this to HV side. Since SC test is connected at the HV side, so refer this. So this can be divided by 10, that is equal to 62.5 amps will be flow in the HV side. This is rated current, remember this. And then next find ZSC. So here you can neglect the shunt branch parameters. Okay, so you can neglect the shunt branch parameter here and consider only series branch parameters. Here if you refer the resistances R2 at the primary, it will get multiplied. So R2 dash is equal to 2 into 10 power of minus 3 into 100. So that is equal to 0.2 ohms will come. And if you refer the X2 dash to primary, X2 dash is equal to 0.45 amps. So ZSC is equal to RE plus J into XE, that is equal to 0.4 plus J into 0.9 ohms will come. So RSC, not VSC, is equal to ISC into ZSC, that is equal to 62.5 into 0.4 plus J into 0.9. So how we will get to convert this to polar form, and we will get 61.5 at an angle of 66.037. So power factor is equal to cos of 66.037, that is equal to 0.4. Lag will come because inductive load. So power PSC is equal to ISC square into 0.4. This is resistance, that is equal to 1562.5 watts will come. This is all about the problem 1. Okay, come to the second problem. This is somewhat tricky because here we have taken a 3-phase transformer. So this is taken from Bimra book. So here first we have to convert the all values to per phase quantities, because we will conduct the test in 3-phase only, but analyzation will be in per phase. Okay, he has given the open circuit test. This open circuit test is conducted on LV side. So LV is 400 volts, but it is at star connected. So V phase is equal to 400 divided by root 3. It will come around 230.94 volts. Okay, this is VOC. IOC is equal to 9 amps. Cos phi naught we have to find, that is equal to P naught divided by 3 into I naught into V naught, all per phase values, because we have taken 3 here. So what is here, the wattmeter reading 1.5 kilowatts. So 1.5 into 10 power of 3 divided by 3 into, what is I naught, 9, V naught 230.94. So what is the value here? So here this value is 0.241. So find sin phi naught. Sin phi naught is around 0.971. Now find IC, RC, and RC is equal to V naught divided by IC, that is equal to V naught divided by I naught cos phi naught. So this value will be around 106 106.47 ohms, and Xm is equal to V naught divided by Im, that is equal to V naught divided by I naught sin phi naught, that is equal to this value around 26.426 ohms. See here, this is all at the LV side. So if you refer these values to HV side, we have to take K. So K is calculated on the basis of per phase, not on the line voltage side. So find the value of K and refer to HV side. So what is the value of K? K is equal to V1 phase divided by V2 phase. So here we are at the primary is taken as HV side and secondary is taken at LV side. So K is equal to, so primary is delta side, so 11000 divided by secondary is at star side and take phase voltages, so 230.94 volts. This this value came at 47.63. So now refer these values to HV side. RC 1 dash is equal to 47.63 whole square into 106.47. Got the values of this value says at 241.54 kilo ohms, and Xm 1 dash is equal to it about 59.95 kilo ohms. This is all about referring. And now come to SC test. Here in SC test he has given V phase is equal to 11,000 volts, I phase is equal to about this voltage is this current I phase is equal to I rated is equal to 200 into 10 power of 3 divided by 3 into 11,000. This is 6.061 amps we have came. Now calculate ZSC. ZSC is equal to VSC divided by ISC. This is 350 divided by 6.061. See here, this is not rated voltage, because VSC is small compared to rated voltage, so not take a rated voltage. He has given VSC means short circuit voltage, that is taken directly here. Since it is at HV side is delta, that's why we have taken V phase directly. Now what is the value here? So 57.74 amps ohms came. Now calculate or E1. So 3 into I1 square or E1 is equal to 2.1 into 10 power of 3. So RE1 is equal to 2.1 into 10 power of 3 divided by 3 into 6.061 whole square. What is the value of RE1? RE1 is came 19.055 ohms. So XC is equal to root of ZSC square minus RE1 square. We have got the value this as 54.505 ohms. Now we have came the equivalent circuit and referred the RI and XM also to the HV side, and now we have to find the efficiency at off load and at unity power factor. See here, if you taken this efficiency eta is equal to 1 minus losses divided by losses plus power, output power, P out. So take these losses as three phase or single phase. You can take either. So if you take numerator at three phase, then we have to take the denominator also three phase or single phase. Three phase. If you take any one, so we will take all three phases. That is equal to 1 minus. What is the losses? Losses we have taken first fixed losses, that is 1.5 into 10 power of 3 minus plus. So it has taken off load. So we have taken off square into 2.1 into 10 power of 3 divided by, so 1.5 into 10 power of 3 plus 1 by 2 whole square into 2.1 into 10 power of 3 plus 1 by 2 into 200 into 10 power of 3. So it will came around 98.02%. This is all about second problem. So if you have doubts, any doubts, you can post your doubts to my Facebook. My Facebook, Rajlinga. So this is my Facebook, or you can post your doubts to my mail, linganl215@gmail.com. This is all about third lecture. Thank you for seeing.